Okay, good morning, everyone. So today we're going to be talking about scattering and specifically about the influence of bound states and resonances, which are not the same thing, in scattering in 3 dimensions. Okay, and so first of all, we're only going to be talking about spherically symmetric potentials today. And so let's say we have such a potential, V of R, and let's say it has a bound state, which it doesn't always have a bound state, even if it's an attractive potential. In 1 dimension, all attractive potentials have at least one bound state, but in 3D, they sort of have to be deep enough. And I guess it could have more than one. So I could say bound states. So a bound state means that the wave function, this is going to be important in a little bit, the wave function has to go to 0 as r goes to infinity. That's sort of the definition of a bound state. And then if you work with the Schrodinger equation for a little bit, you'll realize that that means that the energy of a bound state, as you should have learned in the last homework set, we had one potential and we computed both bound and scattering problems with it. And the bound states have negative energy, whereas the scattering wave functions have positive energy. Okay, so just to draw a picture, let's draw a typical attractive potential, meaning it's negative here. So maybe it looks something like that, and it's going to 0 at infinity. It's got some finite range. And then we could also draw the energy levels. And so if there's a bound state, the energy level is here, let's say. Just like the hydrogen atom, the bound states had negative energies. Whereas if we're doing scattering, we're up here in energy somewhere. Okay, and so they live in completely different energy regimes. Different types of energies give rise to these two different solutions. Nevertheless, what we're going to find out in a little bit is that the total cross-section is affected by the presence of the bound states. Okay, so to see that, let's start with writing down a scattering wave function of the type that we have written down before. And what we're going to try to do with it is to infer what the bound state wave functions look like. So here's our scattering wave function. It's got some factors that are actually not going to be very important today. 1/2 pi to the 3/2. And then there's a sum over angular momenta with a 2L plus 1, which will also not be important today. A Legendre polynomial, like so. And then there was this factor, -1 to the L e to the minus I kr. We've written this in several different but equivalent ways. There's the exponential of the phase shift. And there's our outgoing wave. And this is all divided by 2I kr. Okay, and we should remember this is really only valid when r goes to infinity. That's the form of the wave function at large distances. At smaller distances, when you're inside the potential, then it can be something much more complicated. Right, and because we did this in the case of scattering, the energy, which is h bar squared k squared over 2m, is greater than 0. So how are we going to start with this wave function and try to get a wave function with negative energy? So there's actually a pretty obvious try. What if we just take k and we replace it by I times kappa? So if you do that and you plug it into Schrodinger's equation, if it worked before, it'll still work. But now the bound state energy, instead of being h bar squared k squared over 2m, is going to be minus h bar squared kappa squared over 2m, which is negative, which sounds good. And not only that, but now that we're looking for bound states, we don't have to worry about matching this thing onto a beam that's coming from very far away. That was the thing that required us to have all the different angular momenta in the sum here. But if we don't care about that, if we just want a wave function that works, we can just take each value of L separately. And we know that a spherically symmetric potential commutes with the Hamiltonian, commutes with the total angular momentum, and therefore there are common eigenstates of energy and angular momentum. And so we could use this to attempt to write down a bound state wave function for a given angular momentum. And so now I'm going to dispense with all the constants and just write, it's got to have this Legendre polynomial of cosine theta. And then I also want the dependence on R. So minus 1 to the L. Now I'm plugging in k equals I kappa. So there will be minus 1 to the L e to the kappa R minus e to the I to delta L e to the minus kappa R divided by kappa R. Okay, and then there's some overall constant in front of this, which was the 2L plus 1 over 2 pi to the 3 halves. But we're not going to worry about that. So the main reason we're not going to worry about that is because if we look at this wave function, which was our attempt to find a bound state with negative energy, we realize it has a big problem. And the big problem is this term right here, the e to the k kappa r term. The problem with this is not just not normalizable, but it's horribly not normalizable. So not normalizable, but in a particularly pathological way that the probability density grows with distance. So the probability density is proportional to psi squared. And so that's going to be proportional to e to the 2 kappa r, right? And that says, if I draw some very large sphere with, say, a radius of 10 light years around my origin, then it's still true that my particle has negligible probability to be found within the sphere because it's got a much greater probability to be found outside the sphere. In other words, this sort of wave function will never actually be realistic because it always predicts that no matter where you look for the particle, it's always farther away than where you looked. Okay, so that sounds like a big problem, but there's a possibility of avoiding the problem. So, but what happens if we multiply this thing by a factor of minus 1 over e to the 2I delta L? Let's just see what happens. So that looks like just a normalization factor that we could absorb into the other normalization factors. And so now this thing is going to be our Legendre polynomial. It's just there to give the angular dependence associated with the angular momentum, L. I'm going to pull out the factor of kappa r. And then there's a factor e to the minus kappa r, which was originally this term. And then there's the other term, which is plus minus 1 to the L plus 1 over e to the I 2 delta L, that's an I, times e to the kappa r. Okay, so we haven't really got rid of the problem yet. It's still here. This term is still trying to make the probability density be very large and farther away from the origin. So what we're going to do instead is we're just going to kill that term. Okay, so this term is okay. And this is the bad term. And so what we're going to do is the only way to get rid of that term, minus 1 to the L plus 1, is there's not much we can do with that. But this denominator, we could make the denominator go to infinity. And if the denominator goes to infinity, this whole term will just be gone. And everything will be okay, because we'll just have that term left. So that's what we sort of have to do in order to find a bound state. So we require e to the I 2 delta L equals infinity for a bound state with angular momentum L. Okay, and so the lesson of this is, let's say you're given the potential, you solve the scattering problem, and you find the phase shift for a given angular momentum. Sort of like we did on a previous lecture for the case of hard sphere scattering. In general, it's going to be harder than that, but let's say we've done it. So we've done this for some scattering problem, and it's a function of energy. Then the statement is that to have a bound state, e to the 2I delta L, which is also a function of energy, must have a pole, which is just another way of saying it goes to infinity, for E equals E bound, which is less than 0. Okay, and so we can, given a scattering amplitude, or even if we've measured the scattering experimentally, we can look at the function as it depends on energy and try to figure out where there should have been a bound state. The bound state will show up as poles in e to the 2I delta L, and therefore as poles in the scattering amplitude. But in the scattering amplitude at negative energy, which is not where we actually do the scattering. We always actually do the scattering at positive energy, but then we determine the function as a function of energy, and then we look at negative energy to see where there would be a pole in it. So it's kind of indirect. Okay, so let's remember now how this is related to the actual scattering amplitude. There was this function FL of k appearing in the scattering amplitude. And there were a couple of different ways to write this. When we were doing the partial wave unitarity bound, we found it convenient to write it like this: e to the I delta L sine delta L over k. But today it's going to be more convenient to write it like this. This is exactly the same function: 1 over k cotangent delta L minus I. So you can show those are equivalent by just using the trig identities and using the expression for e to the I delta L. Okay, and so it's that thing is proportional to e to the 2I delta L, and so we should see a pole as being a place where cotangent delta L is equal to I. So notice the delta L for that situation has to be complex, as opposed to scattering where it's always real. Okay, so let's consider in particular the case where L equals 0. And let's consider what happens when the energy goes to 0. And so one thing we learned from examples before is that the cross-section and therefore the scattering amplitude approaches a constant. And therefore it's traditional to parameterize that by saying k times cotangent delta 0 is, so if this thing's going to approach a constant at small k, the k times I part can't matter. So the k time, because that's going to 0, so the k times cotangent delta 0 part has to be going to a constant. And we traditionally call that constant minus 1 over a. And then if we were to expand this, we would find that it's a power series in energy, or differently, we can say it's a series in k squared. So it looks like that. And then the next term will be k to the 4th. And people who do this for a living give these coefficients names. We're only going to name the first two. This defines the a that appears there is called the scattering length. And then the coefficient of the next term, R0, is usually called the effective range, which is very confusing because it's not the same thing as the range of the potential that when we were talking about the Yukawa potential. This is just a different quantity, but it's also called the effective range. And then I forget what the other coefficients are called, but we're not going to use them anyway. Okay, so now we can ask the question, given this, is there a bound state pole? Okay, and so to find out, we're going to take our k and replace it by I times kappa. And we're going to require that cotangent delta 0 is equal to I, because that's what's going to make this thing blow up. Okay, and so let's write down what that implies. That means I has to be minus 1 over k times a plus higher order terms, which is going to turn into minus 1 over I kappa a plus higher order terms. And so that equation is solved if kappa is approximately, I should write approximately here, 1 over a. So that tells us to have a bound state pole, we need for the scattering length a to be positive. Okay, so again, the scattering length is just you in your problem, you solve for cotangent delta 0, you expand in small k, you should find it has this form. And when it does, you pick out this first coefficient. If that coefficient is negative, that means a is positive. And if a is positive, then kappa is 1 over a. So how do we know that has to be positive? It's because, again, the bound state wave function goes like e to the minus kappa r. Therefore, it's going to be going like e to the minus r over the scattering length at large distances. Okay, and we need that to get small rather than blow up at large distances. That's why A has to be positive. If A was negative, it would be blowing up at large distances. Okay, so that tells us if we can measure a scattering amplitude by inferring it from scattering cross-section, and we find a positive scattering length, then that usually means there's a bound state. Actually, not always, and at the end of today's lecture, we'll see why not always. Okay, so in that case, sigma 0 is 4 pi squared over k squared. This is something we had written down before. So it looks like that. And now we can just plug in our expansion for cotangent squared delta 0, and it looks like this. Okay, and so there's some constant in the numerator, and this looks a lot like hard sphere scattering, but A is the scattering length, not the size of the potential. And then in the denominator, we have 1 plus something proportional to energy, but we know this thing has to have a pole at the bound state energy, so we can write this as 4 pi squared a squared over 1 minus energy over the bound state energy, because it's got to blow up where the bound state energy is equal to E. So this is going to be valid at low energies. And so by looking for something like this, you can infer where the bound state should actually be. So one thing to emphasize is that in scattering, the cross-section never actually blows up. And that's just because the E is always greater than 0, but E bound is less than 0. So the denominator never goes to 0. Okay, but you can still infer it from the dependence of the denominator on energy. All right, so all of that was about bound states, and this is what we started talking about last time, bound states are not the only poles. There are other ways to have poles in the scattering amplitude or in the cross-section. So recall that I'm just going to rewrite actually the formula we had above. The cross-section for a given partial wave looks like this. Okay, and then if for some energy you find, so let's call that the resonant energy, because that's what it's going to be. Let's say you plug in that energy and you find out that the cotangent of delta L is as small as it can possibly be, which is 0 in magnitude. Then this partial cross-section will peak. It will be as big as it can possibly be, consistent with unitarity. Okay, and so now if we look at energies in the vicinity of that resonance, right, then this is 0 plus expanding in a series, E minus E resonance. This is just what you get when you do a Taylor series expansion. So if you do the derivative of the cotangent of the phase shift with respect to energy, and you plug in E equals E resonance, that's going to give you the linear term. And then there will be higher order terms that we're not going to worry about. Okay, and what we're going to do is this right here, because we're evaluating it at the resonant energy, it's some constant, it doesn't depend on energy. And so we are going to call this, following tradition, we're going to call that constant -2 over gamma. So if we do that, then up to the higher order terms, cotangent delta L is approximately -2 over gamma, E minus E resonance. And now we can plug that into the sigma L formula that we had. Okay, so all we're doing is we're saying this is our cotangent delta L. Let's plug it in right there. And then let's simplify the resulting expression a little bit. And then sigma L is 4 pi 2L plus 1 over K squared. And then the rest of it looks like a typical resonance in energy. So there's an E minus E resonance squared plus gamma squared over 4. Okay, so what's going on here is this term in the denominator, the E minus E resonance squared, wants to make it blow up. But then the gamma squared over 4 is saying, no, the denominator can't quite be 0. It can't blow up. And so that's a typical resonance line shape. Of course, we could also write the K squared in terms of energy. E equals K squared H bar squared over 2m. But for some reason, it's traditional to keep writing it like that. So now if we graph, what does the cross-section look like as a function of energy? Here's our resonant energy. Okay, and it has a shape that looks like this. Near the resonant energy, it's got a peak, and then it's got tails. So this is the partial wave cross-section. Now for the other angular momenta, there's nothing particularly special going on there. So they're just going to contribute some smooth background to this. And then the other thing we can graph is we can graph versus energy, the phase shift. And because we know the cotangent's going to 0, we know the phase shift is going to an integer plus 1/2 times pi. And so if we pick out the resonant energy here, the phase shift behaves something like this. It goes very steeply through and then it tails off again up here at n plus 1 times pi and down here at n times pi. Okay, and the slope of that line is determined by gamma. Okay, so all of this is just parameterizing what can happen. Our partial wave scattering amplitude, remember, also can be written like this, 1 over k cotangent delta L minus I. And so near the resonance, if you just plug in what we got for cotangent delta L, this is minus gamma over 2k divided by E minus the resonance energy plus I gamma over 2. Okay, so what we found is this peak in the cross-section corresponds to a pole in the scattering amplitude. So the pole is now at E equals E resonance minus I gamma over 2. So it's a pole in complex energy. Another thing to notice about this is, unlike the bound state pole, this pole is at positive energy, but it's at positive energy minus an imaginary part. So this is very unlike the bound state pole, E bound. So just to give an example of what a potential would look like that could give you a resonance like this. So this is an example of a resonance potential. So the general feature that they have looks like this. You have it go to infinity at small r and does something like that maybe. Okay, and then the energy associated with the resonance is positive, so it's up here. Okay, so that's a positive energy. But it's not a true bound state because the energy is such that it's above the potential at large distances. And therefore, way out here, it's behaving like a scattering wave function, not a bound state. So that's why it's not a bound state. Okay, and more specifically, if you write down the three-dimensional Schrodinger equation that has an effective potential part, which is the actual potential, plus the part that comes from the centrifugal term in the kinetic energy, which looks like this. Notice that second term is a repulsive core. And so any sort of attractive potential for the V of R part is going to give you a shape that looks like that, right? And so then your resonance, you think of it as a wave function that's living mostly in this region, but it has some amplitude to live out here also, and that's why it's not a bound state. Okay, so we've seen two different ways that you can have poles. These are poles in the scattering amplitude, or equivalently in e to the I 2 delta L. Okay, and we see them both by promoting the energy to a complex variable. And so the way we can represent this is, let's draw the complex energy plane. So this axis is the real part of the energy. This axis is the imaginary part of the energy. And then we can put a dot wherever there's a pole in the scattering amplitude. And so what we've learned is that on the negative real axis, there are bound states. They live right on the axis. There's no imaginary part. And then below the real part, the real axis, but with negative complex part, negative imaginary part, there are resonances. But if you ask, where do we actually do scattering? That's exactly on the real energy axis. So that's where we actually do scattering. We never actually hit the poles, but we can infer that they are there by the behavior of the cross-section. Okay, any questions on that general stuff before we do an example?
Professor, I had a general question on scattering.
Uh-huh.
So why can't we normalize in scattering?
We can't, because the scattering amplitude is non-zero off at infinity. Right, so bound states are bounded, which means the wave function goes to zero at very large distances. And so we can square that and integrate and get a finite number. But for scattering problems, if we go way back to the beginning of the lecture, right, at large distances, they just oscillate. And so if I integrate over all space, I'm just going to get infinity. So that's why we never actually try to normalize them to unity for scattering amplitudes.
Thank you.
Okay. All right, so let's do what I think is the classic problem that fits into this bound state resonance stuff that we've been talking about. And this is neutron-proton scattering, which has the strange feature that many quantum mechanics books don't quite do it right. Okay, so, and I think that's basically historical because it took a long time to figure out what was actually going on. So you scatter a neutron off of a proton, and out comes a neutron and a proton. We're doing elastic scattering. And you could ask, are there any bound states that we could see this way? And it turns out there's exactly one, which is convenient. There's one neutron-proton bound state that exists. And that's the deuteron. Deuteron has a binding energy, E bound, which is negative 2.2246 MeV. And you could ask, what spin does it have? And since neutrons and protons both have spin 1/2, they're not identical particles, but they both have spin 1/2. And so just adding together two spin 1/2s, they can either have total spin B0 or total spin B1. And it turns out the deuteron is the spin 1 combination. And so the spin 0 doesn't have a bound state. So that's just experimental fact of life. And one thing you learn from this is that the potential in neutron-proton scattering is spin dependent. Because if it wasn't spin dependent, then if you saw a s=1 bound state, you should also see an s=0 bound state. It's also kind of complicated, and we're not going to try to model it. You can do crude models of this potential, but it's really done by the strong nuclear force, and so it's quite complicated. So now you could say, okay, what's happening at low energies? At low energies, people have done lots of measurements of this potential. And so you can measure the cross-section and the scattering length and the effective range, and then the other parameters that occur in that. So this is scattering length. Okay, and so now I can just tell you what the data looks like. So the scattering length in the spin 1 channel turns out to be 5.42 fermions. The effective range in the s=1 channel is 1.75 fermions. 1 fermion is 10 to the minus 13 meters. It's just a convenient unit. And then for in the spin 0, this is the scattering length in the spin 0 channel, it's negative 23.7. And the effective range turns out to be about 2.7. So what can we learn from that? One thing we learn is, remember, if there's a bound state, the scattering length should be positive. So indeed, this is matching what we expect. This is positive, so we expect a bound state. And that bound state is the deuteron. On the other hand, this scattering length for the s equals 0 is negative. And so that's telling you that there is no bound state. So in that sense, the scattering data is telling you what you can already measure in a different way, namely that the deuteron exists and that it has spin 1. So let's do this a little more precisely. Let's figure out the relationship more precisely. So remember that when we had this relationship between the k and then the kappa and the hole in the scattering amplitude. And so that in this case is going to amount to kappa equals 1 over a plus 1/2 r0 kappa squared. And then if we were to do this really carefully, we would want to include the higher order terms. And professional nuclear physics people will go ahead and do that. Oh, one thing I forgot to mention is I said this was the spin 1 channel. It also turns out to be mostly, but not entirely, the L equals 0 channel, the L equals 0 partial wave. So this is mostly L equals 0 partial wave. But the strong nuclear force is very complicated, and therefore it's not entirely L equals 0. It's got a little bit of a mixture of L equals 2. And one way we know that is that the deuteron, if it was all L equals 0, then the deuteron would be spherically symmetric. And that would mean it would not have a quadrupole moment, but it's been measured that the deuteron does have a quadrupole moment. And so maybe I should have put here a small mixture of L equals 2. Okay, so that's the orbital angular momentum. The spin, though, is always either 0 or 1 because each one of the constituents has spin 1/2. So spin 1/2 and spin 1/2 gives you spin 0 and spin 1, period. And so that's why it really does always boil down to the spin 1 combination or the spin 0 combination. Okay, so anyway, that's the kappa of the bound state. And remember, we have the data, so we know what these numbers are, and we can just plug them in. And then we can plug in the bound state energy. The bound state energy is minus h bar squared kappa squared over 2m. So we know all those numbers, and if you just plug them in, it turns out to be about minus 2.22 MeV. Right? And so that number, minus 2.22 MeV, should be compared to this number, to which it's extremely close. So that's showing that all of this stuff works. It turns out that it's sort of accidentally close because the reason it's not exact is a couple of reasons. One is the ... here. The other reason is because it's got a little bit of L equals 2, and we've been pretending it was all L equals 0. Okay, and if you take those two things into account, it actually, the agreement with the actual bound state energy of the deuteron is closer than it had any right to be. So, but anyway, it works pretty well. Okay, and then you can check the total cross section. And this is one of the things that took a while for people to figure out. So the reason is because when you check the total cross section, you have to do it both in the s=0 and the s=1 channels. So let's do it first for neutron-proton scattering in the s=0 channel. And we're doing L=0 as an approximation. And so that's going to be 4 pi times the scattering length in the s=0 channel times over 1 minus E over E bound. Okay, and then you just plug in the numbers. This turns out to be 3.69 barns over 1 plus, remember E bound is negative, so this is 1 plus E over 2.2246 MeV. Okay, and 1 barn. A barn is a unit of cross section, which is about 10 to the minus 28, well, not about, it's 10 to the minus 28 meters squared. It's got units of area. And the reason it's called a barn is because there was an old joke that this, in nuclear physics, the cross sections are so large, they come out in barns, like here it's 3.69 barns. And so hitting a target with that large of a cross section is as easy as hitting the side of a barn. Okay, so that's the s=0 channel, and then there's the s=1 channel, still treating it as orbital angular momentum 0 because it's mostly that. And so this is going to be 4 pi a s=0 squared, a different number. And then the denominator turns out to be, you just plug in the numbers, it's E over 0.0833 something something MeV. Okay, and that number is, it might look like there's a bound state there, but there is no such bound state. So this is not a bound state. It's certainly not a resonance because it would be positive if it was a resonance. Sorry, the pole would be at a positive value. And so situations like this can occur where something looks like a pole, but it's not a bound state or a resonance. And this is called a virtual bound state, not to be confused with a real bound state or a resonance. There are 3 different things. And so one way you can think of it as something that would be a bound state if the potential were just a little bit stronger, right? But so the way it works is if you see a pole, you can't be guaranteed that there's a bound state. But if you know there's a bound state, then there has to be a pole. All right, and so finally, if you say, okay, what were they measuring in the early days of nuclear physics when they were scattering neutrons off of protons? And the answer is, of course, they weren't measuring either one of these 2 things. They were measuring some average. So in fact, what's measured, or what was originally measured, I think they have ways now of isolating the different spin components, is the spin average version. Okay, and so the cross section for neutron plus proton at low energies, the spin averaging is going to be 1/4 of the spin 0 part plus 3/4 of the spin 1 part. And the reason for that is just that the spin 1 is a triplet, as we know from adding angular momentum, and the spin 0 is a singlet, so there's only one of those. Right, so to average, if the spins are just completely random, you have a 1/4 chance of being in the singlet state and a 3/4 chance of being in the triplet state. And then you plug in these numbers from here, and I didn't write down here, but what you can do is plug in the scattering length that I told you, plug in the numbers, and it's just arithmetic drudgery, and you get out 20.4 barns. And that agrees very well with the measurement. Which was a little bit confusing to them in the early days, just because they didn't realize that they had to do the spin averaging, which is, in retrospect, a kind of a simple thing. All right, so that's it for today. We have one more lecture left, and I haven't actually decided what we'll do with the last lecture, so that will be a surprise on Wednesday. All right, any questions on today's lecture? All right, if not, then I will see you all on Wednesday. And watch your emails for information about the take-home final.
Thank you.
All right, have a good day.
Thank you.